Hello everyone, I'm Jesse.
Hi everyone, I'm Lilith. We're from X Lab, Actuated Experience Lab at UChicago, advised by Ken Nakagaki. Today we're presenting our work titled AeroRig UI on actuated mid-air tangible user interfaces for spatial interaction.
Inspired by aerial rigging stage performances, we developed a mobile robot on a ceiling surface that can dynamically control the physical objects in the air.
Specifically, we designed mobile swarm robots, RigBots, that can reel strings to rig objects. Our system can enhance everyday space by creating actuated and tangible spatial interactions. In prior work in HCI, there's already been spatial tangible UI systems proposed with different techniques, such as magnetic or acoustic levitation, drones, and air jets. These opened up a very exciting research space in levitating physical objects in mid-air. But many of them require constant energy to keep the objects in the air, and they also suffer from other difficulties such as noise or payload capacity. String-based actuation has also been explored in previous HCI research, for example, STRAID and SPIDAR, which intelligently use reeling mechanisms for spatial and haptic interactions. However, these systems are often fixed in place and are limited in degrees of freedom to control objects. We also take inspiration in robotics research outside of HCI. The research on ceiling-mounted cranes as well as robots on unconventional surfaces informed us in our research for using ceiling robots to facilitate tangible interaction. We also weren't only inspired by technological research, but also by aerial rigging performances in stage productions, where performers are rigged in mid-air with ropes and strings attached to the ceiling, allowing for their 3D positions to be freely controlled. We believe that the aerial rigging techniques have significant potential to dynamically move 3D objects, allowing them to dance and float in everyday spaces. Combining the artistic inspiration in aerial rigging with the robotics technology, we introduce Aerial Rig UI, an interactive UI providing users with tangible, spatial, and dynamic experiences. In our paper, we offer the following contributions: a general and design space of 3D spatial tangible interactions based on on-ceiling mobile robots with rigging mechanism, a proof of concept implementation to allow people to customize and reconfigure the Aerial Rig UI system, and finally, an application space demonstrating interaction capabilities through practical use cases. Let's talk about the design space next. The basic architecture consists of 5 components: the aerial support stage, RigBots, strings with dynamic lengths, connection points where the strings connect to the objects, and finally, a targeted rigged object. Our system allows for completely different configurations depending on the number of robots. While a single robot can control an object's 3D positions and provide free swinging interactions, 2 RigBots enable constrained swing and haptic interactions. And objects can be rigged for motion control with up to 6 degrees of freedom. With AeroRig UI, there are so many more design space opportunities, including haptic interactions and height affordances, display and visualization, dynamic room installation, and intermaterial interaction, which you can read more about in our paper. To explore the design space, we further developed a proof of concept prototype of AeroRig UI. Our overall system is composed of RigBots, an overhanging ferromagnetic ceiling stage, rigged objects, and as well as software control. The RigBot consists of 2 off-the-shelf Toyo robots embedded inside 3D printed mechanical parts. One Toyo is used for handling local motion on the ceiling, and the other for controlling the string reel. We also put magnets inside the mechanical shells so they can be easily attached and detached from the ceiling. We also developed software for AeroRig UI, which consists of a front-end GUI tool for users to control the robots easily, as well as a back-end robot movement calculation pipeline. Along with the software control, we designed a user workflow for better usability. During the setup and prep phase, users may calibrate the string length and then verify payload safety conditions using our payload tool. Then the user may control rigged objects in real time through our GUI tool.
Fundamentally, string-based mid-air TUIs has some inherent risks and limitations, like payload capacity concerns and unwanted swinging. To better understand where our system stands, we measured and modeled these limitations. We aim to understand the risks of rigbot dropping from the ceiling in different conditions, and how different kinds of movement affect the magnitude of swinging. With the results, we were able to implement solutions to minimize and compensate for the risks of dropping and swinging, which should be useful for future researchers. Now we demonstrate 3 applications to present the capability of AeroRig UI's spatial interaction design opportunities. First, AeroRig UI can be used in room configuration to facilitate everyday interactions. For example, in an office, a reconfigurable surface can divide the space into separate spaces, and the objects can move in the air to utilize the entire 3D space for a more dynamic and collaborative ideation process. Additionally, AeroRig UI can be used to control everyday objects. For example, a ceiling light that could follow the user, a gripper to bring and take away objects, or even an aerial trash can. Second, AeroRig UI can also be used in data representation of 3D spatial points. Here we created a spatial solar system representation that can dynamically switch between geocentric model and heliocentric model. Users can explore and learn about our solar system through the interaction provided by a floating slider or a joystick, which are also rigged by rigbots. We can also physically represent 3D constellations. When overlaid with AR information, it creates a spatial, tangible exploration of the stars. Lastly, AeroRig UI can be used in mid-air animated craft and kinetic sculptures. With hand tracking, users can dynamically control the marionette's actions by their finger movements and control a flapping bird freely. This paper investigated the first step towards enhancing our everyday physical space with rigging up robots on ceiling surfaces. For future research, there are some limitations to be addressed. For example, string entanglement and better control of swinging. In addition, we see many future applications that may benefit from AeroRig UI. For example, what if future dining experiences involve actuated utensils and automated food delivery? What if students can kinesthetically learn badminton and soccer with rigbot's help? We believe that AeroRig UI is only the beginning of a new exciting research space, and we will invite you to explore with us. Overall, AeroRig UI contributes to research in spatial user interfaces by enriching our physical environment with computationally controlled ATUI systems. We hope our contributions of this paper could inform the future researchers.
So here we're at the end of our talk, but before wrapping up, we would like to mention that there's actually another paper from our lab named Throyo being presented in this year's CHI. Throyo introduces a unique approach to offer and facilitate throwing and catching spatial interaction using ceiling mobile robots as well. And with that, I hope you get a chance to check both of our papers and come to our joint CHI interactivity demo in Hamburg. Thank you.